Hi, everyone. I'm Raf. So today I'm going to talk about raster data in Julia. The aims of this session are first to introduce the ecosystem for raster data. And as we haven't had the talk earlier from Martin Visser, I might have to go a little bit over the JuliaEO ecosystem as well to introduce that. And after that, I'll showcase the basics of reading, manipulating, and plotting raster data in rasters.jl, which is my package. There are other packages people can use in the ecosystem, but I'll demonstrate my package. Okay, so first we'll have a look at the Julia raster data ecosystem. The overview org for raster data and for vector data and other geospatial tools is JuliaEO, which Martin Visser will talk about tomorrow, I think. So a GitHub organization is a way of grouping a lot of developers together with a common goal. And the goal of JuliaEO is providing like basic geospatial tools for Julia. So there's about, 10, 15 of us that work together on and off on different packages. Next, I'll get into some actual packages. So I guess everyone here uses GDAL at some point or knows what GDAL is. Is that true? Kind of. Maybe use NetCDF. GDAL supports a lot of raster formats, and it's the most common tool for importing raster data in most languages. So most packages like Raster and RasterIO are just wrapping GDAL underneath. So yeah. And how do we use raster in GDAL? I want to show you a little bit of what Simon Danish was talking about in his talk, in that actually in Julia, we use these auto-generated C binaries. We don't use GDAL from your system. You don't have to install GDAL or NetCDF like you would in Python or in R. In Julia, this is all versioned as a package within Julia. So even if you have your own GDAL, we'll install it again so you have the exact right one. So it's part of the Julia dependencies. So this is one of these packages. Maybe the screen is a bit too small. And this is just an auto-generated package. So normally in Julia, around these packages, we have some kind of tool that's written to be easier to use. And for GDAL, it's gdal.jl, mostly written by Martin Visser. But still, most of the time, we don't use that because it's quite a low-level package where you have to use C calls and deal with pointers. So we use this package called archgdal.jl, ECN's archgdal, which is a higher-level Julian wrapper. So the functions are more like using Julia. You don't have to think about pointers or kind of GDAL errors that can occur. So yeah, this is the GitHub for that package. Oh, I've used the GDAL one twice, sorry. Okay, so another common backend for raster data is NetCDF for like larger multi-dimensional data. Again, we have the same kind of pattern. There's a binary wrapper for netcdf.jl that will provide the basic binaries. And then we have a bunch of packages for reading NetCDF in Julia. There's NC datasets by Alexander Barth, who's sitting over here. And this is a CF standard compliant package. That's the one I use in rasters.jl, but there's also netcdf.jl, and they have various for and against for which one you would use. Okay, a less common data set. This is mostly just meteorologists use this and no one else knows what the hell it is. But it's the same pattern. There's a GRIB reader and a wrapper package for GRIB that's recently been added. And this will soon be integrated into rasters.jl as well. Okay, so I hope you're getting the pattern there where we normally have some kind of lower level C package that we're wrapping as a Julia package. We have a simple wrapper package, and then we have something easier to use over the top of that. So you understand where these tools are coming from. Also in Julia, we have a basic package for reading ASCII rasters recently added. We have a ZAR package and HDF5. for when you have raster data in those formats. I want to talk a little bit about mega disk arrays. This is Fabian Gain's package. He's unfortunately not here, but I work on it a little bit with him. And this is an extensible framework for disk-based arrays in Julia. So it gives us chunked reading and writing of disk-based data, lazy broadcasts. So we can do a lot of operations over disk-based data lazily, and we only read what we need when we want it. I'll show you, I'll demonstrate that later in rasters. Yeah, lets us use larger than memory data sets as if they are regular arrays. So we can operate on 80 gigabyte data as if it's in memory, but it's actually not, it's just on a disk. Yeah, we'll look more at that later, I'll demonstrate it. Now look at some high level raster tools. So up until a few years, maybe 3 years ago, the tools I've shown you was pretty much all that existed. And they're not maybe that easy to use if you just want to load and plot a TIFF file easily. You need quite a few lines of code, or you want to do basic operations. So a few of us have written, actually all the people who are part of this course, we've all written different packages to do this kind of high level raster analysis. There's GeoArrays, which is like an ArchGDAL wrapper that makes it easy to use ArchGDAL rasters. There's YAX arrays, which Fabian Gain's package, which is more for using netcdf and big multi-dimensional files. And then the package I'll focus on for the rest of the day is rasters.jl. This is also a multi-backend package, uses netcdf, GDAL, we'll use grib and a bunch of other things. And it has multi-dimensional indexing like xarray in Python, if you know what that is. So it lets you have large rasters with time series or other dimensions that you can work on. It also has a bunch of GIS tools like you would be used to in RasterIO or rasters. Okay, I'll just give you a little bit of background on the package. So I came into working on this stuff not by being into GIS, but by doing modeling. And I needed a tool that would get raster data into large models easily and generically. I wanted to be able to use netcdf or TIFFs or HDF5 custom formats as if they're all the same thing. So your model doesn't know anything about the source of the data. You just have a package that does that for us. We also were working with multi-terabyte data sets, like a long time series, and we wanted them to be loaded lazily, but have the modeling packages not have to care about dealing with the laziness, just treat it like they were normal arrays. So that's kind of baked in from the start. So Raster standardizes the behavior of these low-level packages. It supports named and indexed dimensions using dimensional data, another one of my packages. Lets us manipulate multi-layered stacks of rasters. And these days it has geo-interface interop. And when I wrote this slide, I was expecting to have already discussed geo-interface in the earlier talk, but we can look at that in the next slide. It also has nice plots, recipes. So here's a little bit of an overview of the JuliaEO ecosystem as relates to rasters. So on the right-hand side, we have all the raster data packages I've talked about. The left-hand side, we have vector data packages like for polygons and points. And in the middle, you see geo-interface. Myself and Martin Pronk, largely in the last few months, have done heaps of work on geo-interface to make it so that you can use all of these packages as if they're the same. You don't have to, we can use shape files, GeoJSON, geometry basics objects, and rasterize them in rasters.jl, and it will work with all of them. You don't have to do conversions or anything like that. So you now can interface with a large amount of the ecosystem. And I'll show you rasterizing and stuff later on as well. Okay, one last thing, just to explain how things are working in the notebooks. I've got a little package, raster data sources.jl, that just lets us download really common data sets like WorldClim or Modus, things like that. So you can just, with a single command, download and load the raster, which makes it nice for demonstrating and for documentation and stuff like that. And we can add more backends to that if you guys have data sources that you use a lot that you want to be easy to download. One more thing, I just want to talk a little bit about these packages and your expectations compared to, say, Python packages and R packages. So when you're using packages in Python, like Raster.io, I don't know, I think it's 10 years old, and it has had a lot of non-focused grants and a few full-time developers. And you have the same in R with Terra. But Rasters.jl, I work on this in my spare time. So the most I've ever worked on this is 1 day a week. Just say it's way easier to develop in Julia than the other languages, so that's possible. But the reality is it's not production tested the way that Python and R packages are. So there's a higher chance that you will find bugs. In Python, there's 1 million users. If in Rasters, there's a few thousand users, there's just less chance that someone is going to have hit a bug that you find already. So just to make this clear from the start, and some things might also be slow or not work how you expect, just because not enough people have tried to do what you're doing yet. I don't use the same workflows you use, so I won't hit it. And if you find any of these things, it's really important with all these packages across JuliaEO and other orgs, make GitHub issues. Anything that's slow, anything that's annoying, anything that doesn't work, don't complain about it, make a GitHub issue, because that's the only way we really know what the state of our packages is and what's working. And normally I'll try and fix them quickly if you do, but if you don't make a GitHub issue, it will just stay broken, essentially, unless I run into it or someone else runs into it. Okay, just so hope that makes that clear. Now I'm going to have a look at the notebook and go through a bit of a demonstration of the package. And you can load this up. This is in the JuliaEO repository now under the one of the folders. You can find this notebook, the plenaries folder. Okay, so we've loaded a bunch of packages: rasters, plots, data frames, raster data sources, GeoInterface, and we can get started. So okay, the first thing I'm going to do is just download a raster to use. This one's already downloaded, so that will probably take longer for you. Yeah? The font size? Okay, thank you for telling me that. How's that? Big screen. What about that? Okay, very big. Okay. All right, so you can run that. And with that file path, bio5 path. So this is from the bioclim data set. Ecologists all know this. Maybe no one here knows what that data set is, but it's like a collated climate index for ecologists. Okay, so you can see here we have a raster object. It's like an array, but it has dimensions, CRS, extent, and a bunch of other things. And we'll go through that more a little bit later. The important thing we can do with it is, wrong thing, plot it. Okay. There's a Pluto bug where the first plot comes up empty. So that will happen a little bit and I'll have to plot twice. That's not normal behavior. It's just the notebook. Okay, so we've made a plot of that raster and it looks pretty much as you expect, similar to in R. It gives us the Y and X coordinates and a heat map. Yeah. We can also load multiple files as a stack. So it's similar to the stack concept in R raster, if you know what that is. So this means loading multiple raster files together as one object, so we can index into them together and work with them together, plot them together. So you can see here we have a raster stack, has dimensions just like a raster, but it's got a bunch of layers: bio 5, bio 7, bio 8, bio 12. And yeah.
Just a question, because in the bio5 raster you have the X and the Y projection. Where does the X and the Y projection come from? Is it?
It's in the TIFF file, yeah. But we'll get on. I'll talk about the dimensions in a little bit. Yeah. So you can see when we plot this stack, we get plots of all the layers. Yeah, and it's just an easy way of overviewing what the data is that you have. Okay. Can also, and what I'll do for the rest of the talk is not actually download these files directly with raster data sources. I'll just use this syntax. So raster stack, world clean, bioclean with the layers I want. I've integrated these packages together so you can just get data with this one line. It's mostly to make demonstrations like this easy and make scripts more shareable. So you can see that just running that line gets the whole raster stack for us. And there's a bunch of, there's like Modus and other backends that you can do this with as well. And people are adding more. Okay, now I'm going to look at, as this question we heard, I'm going to look at dimension wrappers and selectors. So Raster.jl is depends on dimensional data, which gives us these dimension tools where we have named dimensions of an array and we can refer to the dimensions of array by name. We can also index into an array by a lookup index for each dimension. So that can be latitude and longitude. It can be a time series with dates. It can be some other dimension. It can be height, elevation, or some other non-spatial dimension that your data has. So by naming them, it means the order that we use the indices doesn't matter. We don't have to use all the indices we don't care about. We just index with the ones we want. So here, show you what I mean. I'll index into the whole stack here with X and Y. And in the middle, this dot is these ellipses are from interval sets.jl, which is just a way of defining open and closed intervals. So this is a closed interval across 42 to 51 and 27, negative 27 to negative 11. So that means we select that region. And if I plot it, those are the coordinates for Madagascar, if I didn't make that clear. So yeah, now we plot it and we have plot with Madagascar. Does that make sense to everyone? Any confusion? Okay. So just to dig a little deeper in that. So these dimensions are it's just a wrapper type. It wraps some other objects and adds a label to it so we know what axis of the array it comes from. So here it's X over interval sets closed interval of 64. But in the rasters, we also use these dimensions. But here it holds this projected lookup array. We can see, I'll show you the type of it here. So we have a projected lookup array inside the dimension, and Rasters has read that from GDAL. So it's read the projection information from GDAL and the geotransform from GDAL, and it's made it into dimensional indices that we can look up. But we use the same dimension wrappers for indexing and for storing the data. Okay. Now moving on from dimensions, I want to look at rasters. And the thing I really want to make clear in this is rasters are just arrays, and they always are in other languages as well. But normally you have this object that you need to use like as.matrix or some conversion if you want to use it in other packages. You can't just use an R rasters raster in every package in every tool in R. You need to transform it somehow. In Julia, we can normally just use a raster directly in all other packages without changing it. And hopefully, if things work well, you get a raster out the other end. This doesn't always work. There are times where people limit the types, and I'll show you why that works. We'll get a rainfall, a rainfall raster as an example. And let's look at the type. So the type of a raster, this function super type gives us what the inheritance is of a type. So hopefully some of you understand inheritance. So in Julia, we use an object inherits from a super type that may inherit from another super type, and that gives it the behaviors of the things it's inheriting from. So hopefully I'll be able to demonstrate that. Here, abstract raster is an abstract dimensional array, dim array, and that in the end is just an abstract array. So most other Julia packages will allow an abstract array. and they'll do operations on an abstract array. So they won't actually care that what you have is a raster. It will just work in other packages. And that's kind of it's a beautiful thing when it works. I'll show you some other properties of what an array is. We'll look at the parent object, and you can see a raster is really just a wrapper around a regular array. And we have an array of the exact same size with the data inside it, but with no metadata. But rasters can use normal base operations like maximum, skip missing. Can also do broadcasts over them. Normally we have to use this function replace missing before we do a broadcast or something, so we don't multiply the missing values. That's a little bit, that's something that will change in future, but not that important for now. But what I'm trying to demonstrate here is, here we're doing a broadcast over this array with multiplying the whole thing by 0.01. So I'm changing from millimeters to meters, the rainfall values in the array. And you can see the returned object we get, again, is just a raster. So rainfall in meters is a raster again with the same dimensions, the same CRS. So it's passed through this operation and we get another raster at the end. And we can do things like get. We can get the maximum rainfall and the mean rainfall in meters. We can also like plot rainfall in meters. Oh, spelling. And there you go. It's plotted again, but now with rainfall in meters. Okay. And you can do that with any of your own custom functions. You can also broadcast them over the raster of functions from other packages, and you'll get a raster out the other side. So yeah, just to prove that, I'll look at the dimensions of the rainfall object. Here we have X, Y, and a band dimension. And the dimensions after doing some kind of broadcast on it, we still have the same dimensions. So they carry through. We also track the missing value of the array if we haven't replaced that with missing. Often it's much faster not to use Julia missings for some things. So we also track a missing value. Also the CRS, the coordinate reference system data, will remain attached to that array through operations. Okay, and also things like the rasters track the orientation of the array and the way that they should plot. Because say when you get an array from GDAL, it's actually upside down on the y-axis. So if you plot it, it will plot upside down. So what I'm going to try and do is break one of these rasters. So we're going to rotate it and permute the dimensions and see what happens when we plot it. See, it still just plots as the same raster. So it knows which way around it is. If that makes sense. So you can reorder the dimensionality if you need something for modeling, if you need to change the indices for performance, and it will still plot in the right way. So I'll show you, if we plot the underlying parent array raster, we get nothing because of that bug. And we plot it again. And yeah, so this is the actual data underneath. You can see it's backwards and rotated. It doesn't know it's metadata. And so that's what you would be getting if you were just working with raw arrays. But rasters gives you this ability to do these transformations and still know what kind of raster you have. We can write that back to GDAL and it will write correctly with the right ordering. It will work all that out for us. Not the internal array, the raster. Yeah, so let's do that. Oh, I'll write to netcdf instead. Okay. Now we'll read it, that netcdf file. We haven't specified the key because normally netcdf is multi-key, but we should be able to plot it. We have this empty plot bug again. So there you go, same file. It's saved properly and we read it as a netcdf and it knows what it is. It has the correct axes. Yeah. That's the basic idea of rasters.jl. That's the kind of stuff that's meant to work as widely as possible in the ecosystem. Another thing I want to look at is laziness. So Raster.jl has a lot of tools built in for working with larger than memory data or just really big data that you don't want to take all of your RAM. So there's this lazy keyword. It used to be always lazy by default, but it causes some problems. So now it's eager by default and it will load the raster to RAM, but you can force it to be lazy and stay on disk by using this lazy equals true keyword. So here I'm going to get the earth and land cover data set. And this is like a very large, it's not a very big file because it's compressed, but once it's brought into Julia, it's a very large raster. Okay. So yeah, you can see this is 43,200 by 17,520. So that's a huge raster. But it's in a small, it's in uint 8, so that's not very big. And what we'll do is, oh yeah, I wanted to show you this. So before, when we got the type of the parent array, we just saw a regular array, but here you see we actually have this file array. And it has a symbol in there, and actually all that array holds is just the string name to the path. There's not even an open file. So this means we can do operations over thousands of files without hitting the operating system max file limit, which is about 500 often. So you can operate, you can broadcast over, okay. Okay, so yeah, I'm gonna go a bit faster now. So we can see this is 6 gigabytes, but we can just plot it and it won't take that long. It'll take a couple of seconds. Oh, it took me longer than I thought. Yeah, there we go. Oh, and it's empty again. Okay, so we've just plotted 6 gigabytes pretty quickly because it's not actually 6 gigabytes. If that makes sense. I can do this with an even more ridiculous example that I'll try and do faster. This is a whole stack of those arrays. So the size of the whole stack, you can see there is 72 gigabytes, but we can just load it and we can convert them all to float 64. So it is 72 gigabytes. And I'm just going to cut out Tercera and plot it. Yeah, and you can see all of that was pretty fast. We're not actually working with that data set. We're doing all those broadcasts lazily, and then we're just plotting the bits that we need after the fact. Okay. A few other little things. Raster has tables.jl integration, which means you can convert between data frames. You can save a raster to CSV or something like that if you have tables. You can use a raster directly in a GLM or any other model like that, as if each layer of the raster stack is a column in a table. So here we're just going to use that Madagascar raster and convert it to a data frame. And just so you can see something in there, you can see if we filter out the missing values, we have the X and the Y coordinates, the band number, which is always 1 in this case, and the layers as columns in the data frame. So that's easy interrupt. And that will work with all tables.jl packages, like 150 packages. Okay, I want to show you some rasterizing. So another thing rasters.jl does is rasterizing any geo interface .jl compatible geometries, polygons, lines, things like that. First, I'm going to download some country border data. Should be already downloaded. Okay, there we go. And I'm going to use shapefile.jl. or what? I've got something out of order. How did this work before? Okay, I'm just going to skip this one. We'll do more rasterizing in the next one. I'll fix it later. Okay. So instead of rasterizing, I'm going to oh, okay. Okay, so that worked. Okay. Okay, so this should work now. All right, so we'll rasterize. I'm going to get the Indonesian border from this data set. It's just a natural earth data set of country boundaries. And we're going to rasterize it. You can do more complex things with rasterization, but this is just, we're simply filling those polygons in with the value 1. So this fill keyword tells us what we'll fill a raster with. And you can see there it's run. And if we plot it, we get a raster of Indonesia from those values. Rasterization, just as it would work in any other package. And we can plot the Indonesia border around it. Just see that it's, yeah, pretty much the same. The difference in rasterize in rasters.jl to most other packages is that it's all native. So it's not using GDAL. This is all Julia code. So we can customize things and make tools that you can't use in other languages. I had a question over here. Yeah.
Yes, I noticed that the color bar goes from 0 to 1, and I only see yellow.
Because I just filled all with ones. So the zeros are just the empty values. Yeah. It's just how plots a heat map. Always has a color bar. I could turn that off. Okay, what else can I get through? I'll do another example like this. So as well as rasterization, we have like masking, cropping, basic GIS tools you'd expect in R and Python packages. And they work pretty similarly. It's kind of modeled off RTerra. So here I'm going to get the borders for Denmark, Sweden, and Norway, just by filtering them out of this table from Natural Earth. That should have run okay. Yeah. Okay, I'm going to get a climate raster stack from WorldClim. See there, and plot it just to see what we've got. And we're going to cut this down for a particular area. Oh, sorry, no, that's not needed. Okay. So here I'm going to use this mask function, mask, and we're using the climate file and masking it with the Denmark border. So that's going to give us a raster mask to Denmark. So we can plot it, and you can see Denmark's so small that it's just this tiny smudge. So we're going to use this other function, trim, T-R-I-M, and we'll trim all the white space. And here we see we have a plot of the actual area of Denmark and the climate. To make this easier for all those countries, I'm going to write a little function that does that. Mask trim, runs trim and mask. And we'll add a little padding of 10 pixels to the outside. So now I can run that for all those borders, Denmark, Sweden, and Norway. You can see one thing here is the Norway plot is really big because there's some countries in the southern, some islands in the southern hemisphere that they own for some reason. I'll just cut that out. You can see here again, we're using that XY indexing just to index the area that Norway should be in roughly, and we'll trim it out later. So now if we plot this change Norway, there you go, just the country. Now we have a mosaic function, pretty much the same as you get in R and Python. We'll just join all of these rasters together into one raster. And if there's any overlap, it will take the first pixel that it finds. In this case, there's no overlap. You could make it take the last or the mean or something if you want. And we can plot that. So there we go, the climate of Scandinavia. And we can write it to a net CDF so that we've got a multi-layered net CDF, or we can write it to TIFF, but as TIFF doesn't have multiple layers of different types, it'll write 4 separate TIFFs for each layer named after the name of the layer. It doesn't write them as bands because one of them there might be a different kind of floating point in different layers. Okay, I've got a few minutes left, I'll just try and show you some zonal statistics. So Raster does actually really fast zonal statistics, which was completely unintentional. It just worked out like that. So zonal statistics is when we take the statistics of an area of a polygon from the data in a raster. So we want the mean temperature in some country, and we can use zonal statistics to do that. So, and it turned out to be like 10 times faster than doing this in Raster.io in Python. I'm not sure how. Again, we'll use this natural earth data set. Download it if we don't already have it. I already have it. Maybe I've already run this. Okay, so we use shapefiles.jl to load a table and move that to a data frame. And we have polygons for all of these countries. Normally when the screen's, yeah, these countries. Natural Earth has some formatting problems, but yeah. So now we'll we'll just use this WorldClim climate data set we've already downloaded. Oh, it didn't work. Oh, okay. So here I'm going to set the month to be January, and we can do this with dates.jl. We can just use Jan. I could also use July or whatever. And we'll use that month to select these climate rasters from WorldClim and plot them. And then we have all these different layers: T-min, T-max, T-average, precipitation, radiation, wind, things like that. So from this, okay, so I'm going to get the mean of all of these climate statistics for all of the countries in the world in a data set, just as an exercise. So we can run that, and I don't think it takes that long. Yeah, so 6 seconds to get the mean of all the countries in the world over 7 layers. So now we can sort this table to data frame, and we can get things like the coldest mean minimums. Oh, one thing, I forgot to add the climate name. We'll just add the names of the countries so this makes a bit more sense. There you go. Okay, so now you can see, as you would expect, Greenland is the coldest, Russia, Canada, Mongolia. And we've just calculated all of these stats directly from the rasters for those countries. Can do the same for the warmest. And yeah, there's my home country, second from the top. The warmest countries in January. Okay. There's always work happening at rasters.jl, and there's a lot of things being added. We have grid files being a PR for that at the moment. I want to add Mackie plotting and a bunch of other Mackie functionality. More rasterization. There's a pull request at the moment to use reducing rasterize, so you can rasterize lots of polygons together and reduce them. polygonization of rasters. So we have conversion the other way from rasters to polygon, and things you make issues for. The other things that get built besides the things that I want are things that people make feature requests for. So if there's anything that you guys need specifically that Rasters doesn't do, make a feature request and make it really clear what kind of syntax you want, what you want it to do. And there's a good chance myself or someone else will make it. Okay, any questions?
Sorry, someone could you just use a microphone, please?
Yes. So my question is that I know that first programs of the feature, but is there any way that you can use some of it where there's a unlinear mapping between the index and the coordinates?
You mean like with a matrix, or so you can?
So not a matrix where you have to actually like compute a function, go from the index to the coordinates, or from the coordinates to the index. Because at least
yeah.
You work with bigger data. Sometimes you have the data which is not on a coordinate grid. So you want to do some operations on it before transforming it into like an actual coordinate grid.
And so normally you'll need the X and the Y coordinate to do that. So you need the X and Y position in the raster to calculate the coordinates. Is that what you're saying? Yeah. Yeah. So dimensional data, it was written to be able to do that. And Rasters has implemented a bunch of simple cases. So it will work when there's a geotransform. So if something's rotated or skewed, that will work currently. You lose a bit of functionality because a lot of things are harder. It's harder to find where things are with the skew. And it's harder to crop and things like that. But you can have a PR underway actually for handling the NetCDF style, where you have a whole matrix, where there's a lookup matrix where you have X and Y coordinates.
Okay.
Yeah, so it's a matrix the same size as the array. So that's the way they deal with that without to not have a function. But you could also write it to just use a function of X and Y. It's probably not even that much code, but no one has made a feature request. Basically, a bunch of those things is like, those are obscure. I'm working at the 95, 97% use case, and hardcore people will come up with those feature requests later. So, because most people don't work with those files, especially in my field, ecology, we never. So yeah, but make a feature request. We can probably do it.
Thank you. Thank you.
Thanks.
Just quick follow-up on that, I was just the same question, because the full dynamic models, they do by default, their freeze are now. So it's
okay. Yeah. It's a little bit weird to implement if you're going to implement it because of the whole XY nature. We have to do some tricks to group the dimensions and work out which dimensions need to be used together. So, but yeah, we can look at how to do it. The machinery is in place to do it. Yeah.
Maybe to follow up on that, maybe we can define to follow up on that. So, it's also a use case that also controls sometimes some arbitrary, grids. So maybe we can define a type, an abstract array whose elements are defined by a function. So that could be a way to handle it.
Yeah, exactly.
They have some quick way to invert this function.
So if I implemented the NetCDF functionality, what you're saying would work inside of that directly.
Yeah, it would be just a special case.
It would be the special case. Yeah, exactly. Yeah. Any other questions? Okay.
Thank you very much, Rafael. Super interesting question.